Hello students, Dr. Bans here. So far we have done treatment of topics on Fourier series, Fourier transforms and inverse Fourier transforms. Okay, so there basically we completed the whole Fourier transforms requirements in signals and systems. So we're still dealing with signals and systems, and now we're going to take a look at Laplace transforms, how Laplace transforms can also be used as a mathematical tool to analyze signals. Okay, so let me write here Laplace transforms. Okay, Laplace transforms. Okay, so the Laplace transform is basically to convert, okay, signals, okay, from time domain to frequency domain. All right, so from time domain to frequency domain. Okay, so sometimes instead of saying frequency domain, they may say S domain, but basically it's the same thing, to convert from the time domain to the frequency domain. So we have the bilateral Laplace transform. Bilateral Laplace transform. So the bilateral Laplace transform is given by L of t. LT is given by what? LT. X of what? T into this, okay, which is equals to integral minus infinity to what? Infinity. Okay, x of what? T into e exponent minus what? St dt. Okay, so now this signal here, x of t, is in the time domain. So if it undergoes Laplace transform, then it will go into the what? S domain or the frequency what? Domain. All right. Okay. So now here in this Laplace transform, okay, so if you want a signal in the Laplace transform, basically this is the equation you use. Okay, so Laplace transform of f of x of t is equals to this. So this signal, instead of writing lt into x of t, I can also write what? This is what? Laplace what? Transform. Okay, so I can have this one. So now this s here, okay, it is a complex variable. It's a complex variable. So this s here is equals to sigma. This is called sigma plus j what? Omega. So this sigma is a real component. This is a real component. Okay, and this one is what? Imaginary component. Imaginary component. Imaginary component. All right. Okay. So now one difference with respect to Laplace transform and then Fourier transform is that in Fourier transform we only have what? Imaginary what? Component. We don't have the real component. Okay, so that means that the Laplace transform is much more preferred with respect to the number of components it has, because it has the real component and then the imaginary component. But the Fourier transform only has the what? The imaginary component, whilst the Laplace transform has both real component and imaginary component. So the Laplace transform can be used for more to analyze much more what? Signal, okay, as compared to what? To the Fourier transform. Okay, and then this is the how you can represent the real aspect and the imaginary aspect of what? Laplace transform. Okay, so in this place is called imaginary of what? S plane. And here this plane, this graph is called what? S what? Plane. and this is the imaginary axis, and this is the real axis. This is called sigma. And here RE, sigma, another name for the sigma is RE of what? RE of S, meaning real of what? S. And this imaginary of S, IMG, imaginary of what? S, IMG, okay, is also called what? J what? Omega. That's the imaginary what? Axis, okay. And this place is what? 0. So this is called the what? The S plane, okay. This is called the S plane. Now, what we can know is that the Laplace transform, okay, of x of what? T is equals to integral of infinity from what? Minus infinity. X of what? T into e minus st the what? The t. Okay. So this one, okay, we can also break the s into these what? Components. Okay, into these components. So now here I can also write that imaginary, okay, from minus infinity to infinity, okay, x of what? T into e minus, not s, no, e minus what? Now e minus what? Sigma plus what? J omega into what? T, okay, into t the what? The t, okay, the t. Okay, so let me write it again. So please, what I'm writing is okay, minus infinity to infinity, x of what? X of t into e exponent minus sigma plus j what? Omega into what? T the what? The t. And this is equals to, and then this is also equals to from integral from minus infinity to what? Infinity, okay, x of what? T into e exponent minus what? 5 sigma t into what? E exponent minus j what? Omega what? T the what? The t. Okay, so now if you can observe this one, okay, you can see that basically this term and this term, they are very common to what? To Fourier transform, if you can remember from Fourier transform. So I can write this one like this, from minus infinity to what? Infinity, okay. X of what? X of t into what? E minus sigma what? T, okay, minus sigma t. All right, so let me take this one as 1, okay, into what? E minus j omega what? T the what? The t. Okay, so now you can see that basically this one, if you remember in Fourier transform, okay, this is used in Fourier transform and this is used in Fourier transform. The only thing that is not there in Fourier transform is this one. Okay, so that means that you can have Fourier transform within what? Within a Laplace transform. The only thing that is missing within the Fourier transform is the what? Is the real component, this real component. Otherwise, this x of t is within Fourier transform. This e exponent minus j omega t is also within what? Fourier transform. Only this real e exponent minus sigma t is the only component which is missing in what? In Fourier transform. So you can see that if I should take this one as x of t and then add this one to it, basically this one is what? Is a Fourier transform. Okay, so now what I can say is that x Laplace transform, okay, of x of what? T, okay, is equals to Fourier transform, okay, of x of what? T, okay, into e exponent what? Minus what? Phi what? T, okay, minus phi t. All right, because you can see that this one is in Fourier transform, this is also what? In Fourier transform. This is the only thing that is missing in Fourier transform, so I bring it here. Okay, so that makes this expression that makes this expression very what? Correct. Okay, so now one thing that we do in Laplace transform is to find the region of what? Convergence. Find the region of convergence. So here region region of convergence. Region of what? Convergence. ROC. Okay, ROC, region of convergence. So how do we find this one? Region of convergence. Okay, so the region of convergence is such that the Laplace transform should actually obey this particular equation that I'm writing. Okay, should obey the integral of x of t. The integral of x of t. So here x of what? T. Okay, into the real component. Okay, so what is that real component? This is a real component. Okay, this so you take the absolute of it. Okay, so the integral should be less than what? Should be less than infinity. Okay, should be less than infinity. Here is what? The t. Here is the t. Okay, so basically that's how it is like. Okay, so now this is the region of convergence. Okay, so we will see how to be able to work this one in a real example. Okay, in a real example. So now let's go to inverse Fourier transform. Okay, inverse Fourier transform. Okay, so so here inverse Fourier, inverse Laplace transform. Okay, inverse Laplace what? Transform. Okay, so the inverse Laplace transform, x of t, okay, is given by 1 on what? 2 pi what? J into what? Integral sigma plus j infinity, and then sigma minus j what? Infinity. Okay, x of what? S. Okay, into e exponent what? St d what? dt. So this is for the what? Inverse Fourier what? Transform. Okay, so now two formulas are very important to be able to proceed on with what? Laplace transform. That is to find the what? To find the LT. Okay, that is what? Laplace transform of x of what? T, which is the same as what? Laplace transform like this, which is given by the formula infinity to what? Minus infinity to infinity. Okay, which is x of what? X of t into e exponent what? Minus s what? T. Okay, e exponent minus what? St dt. Okay, so this is the first equation. Okay, so then the second equation is what? Inverse Laplace transform. Okay, inverse Laplace transform. So the inverse Laplace transform, which is what? X of what? T. Okay, is equals to 1 over what? 2 pi j into what? Minus infinity to infinity. Okay, x of what? S. The inverse Laplace transform. Please, the integral here is sigma plus j infinity, and here is sigma minus j what? Infinity. X of s into e exponent what? St what? dt. Okay, let me write the formula again. X of what? T is equals to 1 over what? 2 pi j into what? Sigma plus j infinity, sigma minus j infinity, x of what? S into e exponent what? St d what? dt. Okay, so this is the formula for the inverse Laplace transform. You must remember these two formulas. And then another formula is for the what? ROC. So the ROC, to obtain the region of convergence. Okay, for that one also, this is the formula that we use. Okay, so the region of to obtain the region of convergence. Okay, that is the Laplace transform should be absolutely what? Integrable. And to be integrable, we have what? Here minus infinity to what? Infinity. Okay, we have x of what? T. We take the absolute, it should be absolutely integrable, so we take the absolute values. Okay, e exponent minus what? Sigma t, okay, into what? The t, which should be less than what? Infinity. So to move forward, you have to be very acquainted with these what? Formulas. All right, thank you. See you in the next lecture.